If you remember last day, so quick little recap on what we did last day. Last day we did the motor. What are the main components of the motor, Nathan? What are the main components of the motor? Well, you must have a magnetic field. You must have a what? You have your split rings connected to a coil. And you have a supply, nice. Right? You have a supply. Right. And if you have to explain how it works, what are the 4 main steps, 5 main steps are? Yes, we have here. What are the main steps? Number 1, direction current. Number 2. Number 2, the force acted. Number 3, the rules applied. Number 4, directional rotation. Number 5, the how continuous motion is maintained, right? So you have to remember those 5 things. Okay? So I'm going to bring you on the board and your right out. You have to learn that, right? All right. So that was the motor. So basically, the motor was taking electrical energy and giving us mechanical energy. All right. So that was the motor. Today, we are going to go in reverse. Right? And we are going to look at the generator. Right? So what do you think the generator will do? The generator will take mechanical energy and give you electrical energy. And you must have heard about a generator, like in Guyana. There's the works. Right? Right? And the mechanical energy going to give you electrical energy. So do I need a supply in a generator? No, I don't need a supply, right? So I'm going to have to get a supply. Am I going to find a force? Nope, I am going to apply a force. Right? So the generator is very similar, except there is no current being supplied. We're not using split rings, we're using slip rings now. Right? We're using slip rings. Split is when you take the ring and split it. Slip is the entire ring, right? The whole thing. That's okay? So we're going to apply mechanical energy here and receive electrical energy here. Okay? That's the principle behind the generator. We're going to apply mechanical energy and receive electrical energy. In order for us to do that, we have to learn Fleming's right hand rule. Right? That's the last rule, right hand rule. Left hand was the motor rule. Now we're doing the generator rule. Right? So we're doing a new rule. Right? So we're looking at the right hand rule, right? Right, so we're looking at the right hand rule. And the same things you learned in the left hand rule is the same thing we're using in the right hand rule. Right? The right hand rule, thumb is the force being applied. Your first finger is the magnetic field. And your middle finger, right? Your middle finger is the induced current. Right? Yeah. Come on back on the right side. Come on that side. Let's talk a little bit harder. Come on this side. Right. So as I said, right? Well, whenever you move something in a magnetic field, you're going to get current. Right? If you take a conductor and you move it in a magnetic field, you're going to get current. You gotta use those wind-up torchlights before?
Yes.
Right? So you have a torchlight and you have to wind it up for the light come on. What you're doing is you're moving a conductor in a magnetic field. That's all. That's okay? You're moving a conductor in a magnetic field and you're going and get current. Right? That is called induced current because it's not permanently there. That's okay? So we are going to use Fleming's right-hand rule to find the direction of the current being induced. All right? So make a note of that. Fleming's right-hand rule. Fleming's right-hand rule is used to find. Fleming's right-hand rule is used to find the direction of the induced current. David, have you? Fleming's right-hand rule. Fleming's right-hand rule is used to determine the direction of the induced current when a conductor is moved through a magnetic field. When a conductor is moved through a magnetic field. Right? Before I show you how to use the rule, I just want to make sure you understand what's happening here, right? Let's take a look at this small simulation here. Right, let's look at the simulation for what this one kind of wonder if you see this one, right? All right, what is simulation here, right? It just giving you an idea of how it will work, which one is the look. That's put on it, but that's not this one. Right, this one. Almost all I'm thinking from. Right. So right now, this one is the opposite, right? I don't think I'll get to move this. Right? Yeah, I will. Okay. So I have a conductor here. Right now, no current in it. You're seeing that? No current in it, right? Because the bulb not lighting up. And I have a magnetic field here. You're okay with that? So what I'm saying is that if I were to remember there's a magnetic field all around here, right? Watch it. See that? There's a magnetic field all around there. So if I were to move this conductor in the magnetic field, I should get current here. The bulb should light up. All right. So let's see if that will happen. I'm just taking off this with this track, right? Moving this here, move now. See that? As I move it, you see the current being induced. See the bulb lighting up. So it means that whenever I move a conductor in a magnetic field, again, current. You might recognize the faster I move it. You see how bright it is. If I do it slow, it's not lighting up that much. But if I do it fast, it would lighten up more. right? And there's a guy named Faraday who explained why that happened, why it lights it up. That's okay? Faraday would tell you, right? Right, so basically, right, once a conductor cuts a magnetic field, you're going to get current here. Okay with that? The generator was the other way around, right? But today we're focusing on the, the motor was the other way around. Today we're focusing on the generator. Everybody okay with that? Right. We need to learn how to figure out the direction of current, right? Come back and watch out. Right. We need to learn to figure out the direction of the current. So we're going to use the right-hand rule, right? So I want to show you an example. So I have a magnetic field. Magnetic fields move how again? Magnetic fields move from north to south. I put in a conductor in here, but the conductor has no current in it. So I'm not putting a dot or X. All I am doing is applying a downward force here. That's okay? The objective of this exercise is to figure out the direction of current. Right? For those who knew, dot with a circle means current coming. And X means current going in. Right? So if the current going into the whiteboard, X. If the current coming out of the whiteboard, dot. That's okay? Yeah. Now yeah. So what we're gonna do now is use the right-hand rule to figure out if I'm putting a dot or X. Okay? You have to use your right hand, okay? So here's how it works. Magnetic field and apply the force. And I am going to figure out what this is. So all you're moving is your wrist, right? You're not moving your fingers, you don't want them to end up like this, right? You want them to stay like this. Ready? So the magnetic field moving how? Towards me, right? So north to south. Magnetic field going north to south. What direction is the force? Down. So this finger have to stay pointing that way, and your thumb have to go downwards. See that? So your first finger going that way, your thumb pointing downwards. So your middle finger pointing out. Out. So which one are you using here? Dot or the X? You okay with that? Copy that down?
No.
Right, so that's the way we use Fleming's right-hand rule. Not grip ruler, right-hand rule. Watch it again for those who weren't paying attention. Right? Magnetic field, north to south. Right? And the force pointing downwards. Right? Remember, you're just moving it, keeping your fingers like this, right? And you're moving it around. Okay? Right, so the force is downwards, but we worked out the current to be north to south, down, current coming out. So your middle finger pointing outwards. So you're using dot in the middle. That's okay. Try number 2. Let's leave it north to south. But instead of putting the force down, let's put the force upward. Work it out. Write the answer in your book and I'll bring it on the board. Please use your right hand. It works and nothing else. It only works using your right hand. Right? If you're new, you'll get a chance on the board too. Huh? Can't go with that one.
I will find a lot of physics.
Take your time.
So the force was where the couple of those points. And that's it.
What's the point of this whole exercise?
Not you. Yeah.
Right, all the lab books available, try and get them now. If you wait till the next set, that'll take very long. Right, so go on my lab book one time, it just take people time. Go on, right? Buy a lab book one time. After you do this, go in the office. Never is it? Right, ready? Right, who's the last person today? Anya.
Okay.
Huh? Next one, you're getting next one. Come on, you. Do it first and you'll join them and then show how they go. Like excellent deduction. What you get? Right, so them how you get out. Magnetic field north to south, south. So watch it here, right? Oh, show them again. Right? Try to let your finger go up, right? Right? So magnetic field north to south, the force is upwards, so therefore current going into the whiteboard. N is X. Very good. That's okay. Next one, I'll pick somebody else. Online, I want you to send the answer for this one, right? Same thing. Online, send the answer for this one. Yeah. Right here. Who want to come and do this one? Who? David, yeah, come to David. Boy, David will get chapter. Right, so David said X, right? Let's see if that's correct. Magnetic field moving from north to south, so that's down. The forces towards me, right? Magnetic field going north to south, forces towards me, so the middle finger pointing inwards. So the answer is X. Last one. Last one, I'll pick somebody. Right, come please, yeah. What's your name again? Next is Solario. Josh. Go. Yeah. Put his symbol and come away again. Dot. Some away again. Magnetic field going up. So your thumb pointing out. I mean your middle finger pointing out. Go back again. You did it correct so far. Your middle finger pointing out. You know. Very back. Your middle finger pointing into the whiteboard or outside the whiteboard. Something X. Yeah, that's right. Point. X. You okay with that? Yeah, X. Everybody okay with that? Right. So now that we could use the right hand rule, let's see if we can see how the generator works. All right. Online, you're okay with that? You're okay with how Clement's right hand rule works? Right. No, I don't like yours. Yes, I like yours. Right. So what you say? Hey, to run. How is background? How do you start over? Right. What you say? Looking at it correct? Right. So you would see it correct that we have a magnet, right? With a magnetic field in the middle. You're okay with that? There's a magnetic field in the middle, right? And that coil, this coil is going to be moving in a particular direction, and it continuously cutting the magnetic field, right? What you see. And because it continuously cutting it, you're seeing it, cutting it there. You'll see a little current being generated. You're seeing that? Yeah, so that is the principle of how the generator works. These rings, you recognize the rings are an entire circle, not half, right? So the ring is an entire circle connected to this rectangular coil that is continuously turning and cutting the magnetic field lines. You see that? And as a result, we have lights here. Right? Is there a galvan? What is the galvanometer? Right. So look at the galvanometer now. All the galvanometers showing you, it's showing you that there's a continuous supply of current. At one point, the current on the right side, the next point, the current on the left side. Right? For those who remember, the galvanometer tells you what direction current flowing in. What I'm looking perfect, yeah? Right? So at one point, the galvanometer telling it negative, next positive. Negative, positive. You're seeing that? So current being supplied, but at one point it's negative, and at next point it's positive. Anybody could tell me what type of current is that? Very good, alternating. So that generator is producing alternating current. Alternating current. Look at it. It is a continuous change of current. So it produces a continuous, produces a negative charge, then a positive charge. The negative means one at one point, current going this way, and the next point, current going this way. Remember, alternating means it just change in direction. Huh? Yeah, we're going into the Y. We're going into the Y. You're okay with us? So that's the way the generator works, right? But before we explain the generator, we have to learn two rules, right? So underneath this, I'm going to head up Faraday's law and Lenz's law. Lenz. Faraday's law and Lenz's law. Yeah? You got that part. That's all. Yeah, buddy. So if the Java lab here. Ah, beautiful. What you saw. It didn't really give me the next part, right? Right, but there are two laws there that we need to understand. The first law we need to understand is called Faraday's law. Hear what Faraday said. Faraday said that if I have a conductor, I'm moving on again. That's all right. All right, here's what Faraday said. Faraday said that the faster, notice there's a magnet here, there's a conductor here, right? Faraday said that the faster the conductor cuts the field lines, the greater the current induced here. All right, so watch this here. As I move the magnet inwards, watch it good. You'll see what happening there. See a current being induced, right? So Faraday said that whenever field lines are being cut by a conductor, current is being induced. And Faraday said the faster it happens, what will happen as it happening slow? Slow. Real small current. See the little red dots around it? And if I allow it to go faster, what's happening here? See the bulb right See the bulb a little bit brighter. Watch around the bulb. You see some red dots? Yeah. So the faster the magnet moving in and out, the bigger the current. Right? And Faraday said that the faster that magnet moves in and out, the bigger the current, right? If I speed it up more, watch out what happens here. Look how the bulb lights up even more. You're seeing that? That law is Faraday's law. But look at that. Lenz, on the other hand, Lenz allows us to figure out the direction of the induced current. Watch out there. At one point it's going down, next point it's going up. Right? And I will show you Lenz law a little bit closer, a little more in depth. I'll show you how Lenz law works, right? But you're seeing that as it going in, it's coming down. As it going out, it's going up. You see the current direction all changing. Yeah. So Lenz allows us to figure out the direction of current. Okay, and I'm going to show you that now. You're okay with that? So we're looking at two laws today, and those are the two laws that explain the generator. Lenz law and Faraday's law. All right. So head up Faraday's law first. All right. So let's look at these laws before we do anything, right? Right, Faraday's law. Hear what Faraday said? Right, Faraday said the faster I move this magnet in and out of this conductor, the bigger is the current being induced. That's all. All right, that's all Faraday said. The faster I move this magnet in and out of here, the greater is the induced current. Okay, so write that down. Faraday's law states that. Faraday's law states that. Faraday's law states that the faster a conductor, give it the right hand. Faraday's law states that the faster a conductor cuts the magnetic field, the faster the conductor cuts the magnetic field, and you're okay, right? The faster the conductor cuts the magnetic field, yeah, the greater is the current induced. The greater is the current induced. Right? The greater is the current induced. Right? So again, the faster I move this in and out, the bigger is the deflection. Remember, this is a galvanometer, right? So a galvanometer tells us how big the current is and what sign current is. The galvanometer does not tell us the actual value, right? So the faster I move in and out, the galvanometer will go, right, further down on either side. That's okay? So the faster I move it, the faster or the bigger the deflections. Okay, yeah. If the magnet just stays there, it's not cutting the field line, so no current. Okay. Right. Full stop. Full stop. Draw this diagram, and I want to give you something small underneath. Draw this diagram. I want to give you a small note underneath. Small thing. About 3 lines long. Or 4. Maybe 5 or 10, how you write it. Maybe you say. Right, we're going diagram. Right, on the diagram, right, this the faster the magnet moves in and out, the faster the magnet moves in and out of the solenoid. The faster the magnet moves in and out of the solenoid. Or then we have no class on Sunday, right? Yeah, we're happy with it. Yeah. Everybody had to look up on. Yeah, no class on it. Right? The faster the magnet moves in and out of the solenoid, the greater is the deflection on the galvanometer. The greater is the deflection on the galvanometer. Right, for those who weren't paying attention, this thing here is a galvanometer. So all that will happen, Nathan, all that will happen is this. It will come down more. That's it, right? It will deflect more. So the faster you move it, the bigger the deflection. The slower you move it, the smaller the deflections. That's okay? Right. So Faraday's law, Philippa, Faraday's law gives us an idea of the magnitude of the current being induced. right? Why do I use the word induce? Why do I use the word induce here? Is that current in here permanent? No, it's temporary, right? All right, so the temporary current in there. So that's Faraday. Faraday gives us an idea of the magnitude, how large it is or how small it is. Now the next guy, named Lenz, he gave us an idea of the direction. Okay, this law a little bit harder, so I want you to draw these two diagrams, am I right? Olha, just take a look at this here. Here's how you figure out how the galvanometer, how the solenoid turning, right? Solenoid turns like this. You can see it look there, right? Solenoid, the solenoid turns like this one. Somebody send a message here. Yes, oh, Annelie, keep me attention. Good job, Annelie. Right? Watch this here. So it's going up like this, and then it curling like that. You see that? So it's coming out here, going in here, and so on, right? You see that? So it's going up here, it's curling here, it's coming back up here, going down here, coming back up here. You see that? You try and make sure your loop behaves the same way. Okay? So it's coming up, then it's coming back down, then it's coming back up, and so on. Right? Make sure your loop behaves the same way. Okay? Draw those two diagrams and let's see if we can explain Lenz law.
And
All right, ready? So when you finish your diagram, I want to explain how we're going to apply Lenz, right? Lenz observes something, right? Lenz observes that the direction current always opposes motion. All right. After you draw a diagram, underneath, I want to write something, right? I want it to write this. Lenz observed. Lenz observed. Lenz observed that the direction of the induced current, the direction of the induced current always opposes motion. Always opposes motion. And I'll ask you why later on, right? So think about it as it's going along, right? Why I think that law applies. All right, ready? So I want to explain the first one to you, right? Here's how it works. Let's say the magnet moving in, because remember the magnet either moving in or coming out. That's okay? So let's say the magnet moving inwards, right? What magnetic pole has to be induced here to oppose the motion? Oppose motion means I want to go in, but it's pushing me back out. What pole has to come here? North. That makes sense? So a north pole has to be induced here and a south pole here. That's okay? You all remember we did the right-hand grip rule for a solenoid, right? And I showed you that the thumb points towards magnetic. What? Thumb points towards magnetic north, and the fingers point in the direction of the current. That's okay? There we are. Yeah? So your thumb now going and point towards the well, don't need that, right? Right? So but they ain't going anywhere, the computer wants to.
So I can't see from here.
Right, so watch this here. Right? So your thumb points towards magnetic north and your fingers curl in the direction of the current. So where is north? North is here, and my fingers are pointing, coming up like that. Right? So my fingers coming out at the bottom and going in at the top. You're seeing that? Everybody seeing that? So how do I show that here? And coming out at the bottom and going in at the top, right? So it going in at the top and it coming out at the bottom. And going in at the top, coming out at the bottom. You're seeing that? So it coming out here, it going this way, and going this way. Eyes up. Seeing that? You sure? So with thumb pointing towards magnetic north and my fingers curling, right? Curling curl in at the top and coming out at the bottom. In, out, in, out. So it's going in up. All right. Clockwise direction. Right? So you have to learn now how the galvanometer will behave. The galvanometer, the arrow, always follows the direction of current. Right? So it's going and go this way here. Okay? So the galvanometer always follows the direction of current. So it will go in that direction. But okay with that? So that is when the magnet moves in. So now, everything that you learn, I want you to try to figure out now what will happen here when the magnet moving outwards. Right? See if we can figure out the direction of the current and the direction of the galvanometer. Don't just assume, I want you to figure it out and see if it makes sense, right? You use your right hand rule and thing. Okay? Use the rule. See if we can figure out what will next is and what direction the current will be in. Remember the magnets moving outward. So the induced magnetic field, want to pull it inwards. All right, let's see what you got, right? Right, so basically, here is not the magnet want to leave, but the coils want to pull it back inwards, right? So if here is north, what has to happen here, Rima? Come on, this one. Here has to be a south and here has to be a north. So your hand, right hand rule, thumb points towards what? Magnetic north, and your fingers point in direction of the current. So the current what? It going coming out at the top and going in at the bottom, right? So it coming out here, coming out and going in here. Right? So it switch around. And it will go this way. Why do I know? You gotta pay attention to this. This could be kind of confusing. So that's why you have to make sure and draw your loops properly, right? Oh, so the magnet going out, right? So based on Lenz's law, it wants to oppose the motion. So if the magnet going out, what's the opposite of out? In. So what pole has to happen here for this to come back in? So, yeah. Right? Are you okay with that? Right, please don't let it off because they can switch this on you. Okay? They can switch this on you. Make sure you understand the concepts. All right. So when it's going inwards, current direction. When it's going outwards, current direction. So you'll recognize the current direction or changing. That's okay, Raj? Yeah. So what does that mean, Raj? What type of current this setup producer. Direction I will change it. So what kind of current is that? Right? That is alternating, right? 1 minute it's going positive direction, next minute it's going negative, then it going back positive, then going negative. That's okay? All right. So Faraday Lenz. Now we have to go back and explain generator using all these rules. All right. I will draw my lane diagram here. But I want to upgrade and do something better. That's good. Right. So you want to explain the way the generator works. Again, what are the things the generator has? Magnetic field. Coil connected to got little brushes here. And we have a load, right? We have a load. And we have a voltmeter telling us the direction of the currents and voltage, right? Actually, you don't need the carbon brush anymore. Right? You can draw them as full circles if you want, right? Right? Please remember that these are slip ring. This and this. It's not half a ring, right? Right. But watch this, right? The force that I am applying to this circuit, I am applying a force that will cause it to turn anti-clockwise. Right? So for this to turn anti-clockwise, the force here is downwards, and the force here is upwards. Everybody see that? Everybody understand that? Right. So I want to explain how it works, right? Do a little sketch quick. This is not as popular, but can someone have social logging out of this Google Class? I don't know. Yeah. Oh, you can come back. Right, do a little sketch and then let's see if we can explain, right? Although you'll have to get your email to be added to the elements this week here. But I'll take out whole class and we get to go online and log on. What have we done? Right, let's see who came today. Lindsay came, Ryan online, Daniel. Daniel here? Daniel here, boy. No, Daniel. Right, Elijah. Elijah not there. We're online. Serena. We're online. Jamie here in the corner there. Lorena.
Same thing they have it, I run it.
Lorena there. Isaac with Maxwell, will come this one. All right. So now you watching football in school. They are in school. the drainage beyond upside down Greek and math. Alex, that Severa, Rima, Devana, the reaction, not paying attention as well. Theta would say that. Theta. Theta. Say that. Yeah, I didn't come. The lines were on the phone of the world. Ashton is come. Ashton is coming.
Hey, bitch, if you try to look sexy for your man's
Dan team corner there.
it's where you feel it more in your biceps, more than that back. Bitch, let's fix that. All you bitches do this mistake of.
Narayan, I hear you, boy. Narayan. I'm gonna call him a mother now. Narayan, trying to do your work now, boy. Borrow here. Narayan on the phone or something. And Ali up. Oh, did you wrong? Ethan. Right, that's four. Ashley. Eden, Chelsea online. My current now cut like 3 times. Right, Israel here, Craig here, Anya on the phone, Calista in the back on the phone, Jamari. Jamari, where? That was the last name? Oh, sorry, Chelsea. Sorry, Chelsea. Jamari, he didn't come. Cathy. Raj, Ijaz still drawing there. And Daniel, Abdul, wait, no, in this one, right? Daniel Mitchell, Kayla. Kayla. Caleb. All right, fix up the rule there. I don't know who Caleb. Right, so we want to explain this. All right, we want to explain how the generator. This is called, make a little note. This is called a simple AC generator. Simple AC generator. Why? Because it's producing enough. Why till it's not? Why is it called a simple AC generator? Because it's producing enough AC current, right? All right, so here's how it works, right? Here's how it works, right? When we connect up the circuit as shown, right? We apply a force in a clockwise direction on coil. So it means that here is downward and here is upward, right? So by Fleming's left hand rule or right hand? Right hand, right? By Fleming's right hand rule, we can find the direction of the induced current. Anybody can work it out for me? Use Fleming's right hand and tell me what direction the current is here. Either up or down. Down. So magnetic field, north to south. The force here is downwards, right? You're seeing that? So the magnetic field going that way and the force going inwards like that. That's okay? So therefore the induced current coming down from B to A. You're seeing that? Magnetic field, north to south, force. Remember the force on this side is downwards, right? So the force is downwards, therefore the current is going B to E. You okay with that? You sure? It does? So if you had a guess, it does. Current going here, how? Up or down? Going down here, so it should be going up here. You okay with that? Raj? Right? So the current going in this direction. You okay with that? So we use Fleming's right-hand rule to figure that out. Are you okay with that? Right? And we have one slight problem though. Right? Here's the problem, right? On the first cycle, current moving from D to C to B to E. Are you okay with that? Yeah? What's going to happen here? First cycle. So it starts here. Right? It starts here. It reach here. Now it's going on the next side now. Right? So we turn it like this. Here getting a downward force, here getting an upward force. So it reach here. That's okay? What you would recognize is this side, which is CB, CD, and on this side. You'll see that? Watch out what happened here now. It's a little bit different to the arm. It's a little bit different to the right. It's a little bit different to how the motor was, right? Now, I still have a downward force here. I still have magnetic field going that way, right? Magnetic field going north to south, and magnetic field going north to south, and the force going down, right? So therefore, current coming from C to D now. Current coming down like that. Current going up here, right? So on the second cycle, what we recognize? Current going from A to B to C to D. So what does that say there? What does that say here? Isaac? Current what? Switch directions, right? It going DCBA, now we're going ABCD. So current switches direction. See that here? Current going positive, then current going negative. That's okay? So you have to be able to explain both cycles, right? During the first cycle, it's going like this. During the second cycle, it's going like that. That's okay? That's it. Okay? You don't have to worry about inertia and thing here in this one. You okay with that? So write this down, write this, and let me give you the explanation. I want to give you the explanation, and that's it for this generator. Ready? Ready? Take this small note, right? Take this small note. The generator works on the principle. The generator works on the principle. The generator works on the principle of converting. Works on the principle of converting mechanical energy into electrical energy. Works on the principle of converting mechanical energy into electrical energy. Full stop. When a force is applied, when a force is applied, when a force is applied, and yeah, right in your book, please. When a force is applied to the rectangular coil, when a force is applied to the rectangular coil, by, sorry, take off by, through the magnetic field, sorry about that. Through the magnetic field, through the magnetic field, comma, by Faraday's law, a current is induced. By Faraday's law, a current is induced. Um, by uh, by Faraday's law, current is induced. Full stop. Right, making sure it's on the and let's read. So we reach Faraday's law, right? Full stop. By Fleming's right-hand rule. By Fleming's right-hand rule. By Fleming's right-hand rule, the direction of current is found. The direction of the current is found for both cycles. For both cycles. But note that the slip rings, causes the induced current to be alternating. Note that the slip rings causes the induced current to be alternating. Alternating. Anybody can guess? Suppose I wanted it direct. What to do? Anyone guess? What we could do? Any guess? Yeah. Remove the slip rings and put what? Split ring. Right? Right? So make a note of that. To convert from alternating to direct. Those who need laptops, please go in the office and get a laptop now. Okay, so I'll class finish here. To move from alternating to direct. To move from alternating to direct. You switch, you split, sorry, you slip rings with split ring. Split ring with slip rings. Slip rings. The slip ring with split rings. Take off the slip and put the split. You know what I mean? The minute one, you put in those and make sure you're right. Last thing in magnets that we'll do next week is something called transport. All right. But I had to find a way to give all that a quiz one.